Welcome to The Explainer. Today we're diving into a concept that might actually completely change how you view the technology that's defining our era. If you follow tech news, you probably think AI is just this recent Silicon Valley invention, a sudden explosion of neural networks and massive data centers, right? But what if it isn't? What if AI is actually the ultimate crystallization of a 6,000-year quest? Today, we're going to uncover the hidden origin story of how 6 millennia of human thoughts, philosophies, and honestly minor innovations steadily paved the way for the creation of an artificial mind.
So when was AI actually invented? Go ahead, seriously, just take a guess in your head. Is it 2022, with the whole generative language model boom? Or maybe you're a bit of a historian and you're thinking of that famous 1956 Dartmouth conference where the term artificial intelligence was first coined. Or maybe you're pointing to Alan Turing in 1950 when he famously asked, "Can machines think?"
We'll prepare for a shock, because the conceptual architecture of artificial intelligence, the actual fundamental ideas required to build it, began right here, 3964 BC. I know, that is a massive reframing of the origin story. We're not looking at a sudden tech leap in the 20th century here. We are looking at millennia of groundwork. The urge to capture reasoning in symbols, gears, and eventually code, it's literally as old as human thought itself.
Okay, let's dive into this. Here's our roadmap for The Explainer. We'll start with AI's hidden origin story, pull apart Thread 1, formalizing thought, move to Thread 2, mechanizing calculation, explore Thread 3, theological guardrails, and finally, bring it all together in the 1943 convergence.
Section 1. AI's hidden origin story.
Let's look at 1943. You've got these two incredibly brilliant yet unlikely collaborators at the University of Illinois, Warren McCulloch, a neurophysiologist, and Walter Pitts, who was this self-taught math prodigy. Together, they published a paper successfully creating the very first mathematical model of a neural network. They proposed that a neuron's firing could act like a switch executing a logical proposition. But here's the secret. McCulloch and Pitts, they didn't invent these concepts from scratch. They didn't just wake up and suddenly dream up binary logic or computational modeling. They were merely assembling the final pieces of a giant puzzle that civilizations had been desperately working on for absolute eras.
Section 2. Thread 1. Formalizing thought.
Because think about it, before you can build a machine that thinks, you have to figure out how to turn abstract, messy human reasoning into rigid, predictable math and procedures. Which brings us to the ultimate building block of computation, the algorithm. Now, an algorithm is simply a repeatable, mechanical procedure for producing a correct answer. And the word itself comes to us from the 9th century Islamic Golden Age scholar al-Khwarizmi, who formalized algebraic procedures. His work laid down the premise that reasoning can be captured as an explicit, rule-governed procedure. So the DNA of the code running on your smartphone right now, it traces directly back to the 9th century.
But actually, the procedure goes back even further. Look at this Babylonian algorithm from roughly 2000 BC for solving a quadratic equation. An ancient scribe, literally working on wet clay, didn't need to know the deep theory of why this worked. He just followed a fixed, step-by-step operational sequence, fully trusting the procedure to output the correct answer. And this Bronze Age procedural logic perfectly mirrors the algorithmic logic inside modern AI training loops today. It is the exact same fundamental concept. Take an input, apply a rigid set of operations, and get a reliable output.
Let's move to and see how this builds throughout history. In 350 BC, Aristotle gives us syllogistic logic, essentially the first formal inference engine, which paved the way for rule-based AI. Then, over in India, around 500 BC, Panini maps out Sanskrit grammar using an ordered system of generative rules. It's strikingly similar to the computational linguistics we use in modern natural language processing. And jumping to 1854, George Boole reduces logical reasoning to an algebra of symbols where truth values behave like the numbers 0 and 1. This whole formal thread is just this progressive shift from messy human thought to systematic mechanical rules.
Section 3, Thread 2, Mechanizing Calculation.
All right, so we've got the abstract rules of logic, but abstract rules kind of need physical hardware to run on, right? And we can trace a real rhythmic progression here. We start around 2700 BC with the abacus, humanity's first attempt to externalize arithmetic from the human mind onto a physical device. Fast forward to 1837, and Charles Babbage designs his analytical engine, this mechanical beast of gears with a memory store and a processor, mapping out the architecture of a general-purpose computer a full century early. Finally, in 1941, Konrad Zuse builds the Z3, the world's first fully programmable electromechanical digital computer. The hardware substrate of AI didn't happen overnight. It was a multi-millennial engineering project.
And this brilliantly illustrates how interconnected our history really is. The Indian scholar Pingala worked out a system remarkably similar to binary mathematics around 200 BC, thousands of years before we had electrical circuits. The Jacquard loom in 1804 used punch cards to program weaving patterns, which directly inspired the physical software memory of early computers. Even cuneiform writing in 3200 BC established the concept that thought could be externalized as discrete, manipulable tokens, which is exactly how today's massive large language models tokenize text process it.
But all this physical mechanization brought up a massive philosophical question. Back in 1843, Ada Lovelace profoundly noted, "The analytical engine has no pretensions whatsoever to originate anything. It can do whatever we know how to order it to perform." She was literally the very first to ask the question we are still fiercely debating right now. Can a machine actually be creative, or is it merely combining what we programmed into it?
Section 4, Thread 3. Theological guardrails.
Now, what's really interesting about this slide is how, long before we had microchips, humanity used theology and mythology as the earliest frameworks to rigorously debate the ethics, limits, and dangers of creating artificial minds. Notice the structural parallel here. On one hand, we have the modern AI alignment problem, the massive challenge of bounding an incredibly capable AI system within safe constraints so its values don't drift and cause a catastrophe. But look at the ancient Genesis narrative. We see the original alignment story. A highly capable agent, a strict safety constraint regarding the tree of knowledge, a persuasive argument to bypass that constraint, and a catastrophic value drift when the constraint fails. We have literally been grappling with the structure of delegated power and runaway agency for thousands of years.
And you can trace this cultural and ethical exploration right through history. In the ancient Genesis narrative, we see the concept of humanity made in the image of a creator, sparking debates about what it means to imbue matter with a mind. In the medieval era, the Jewish legend of the golem explores the sheer fear of an animated clay figure behaving unpredictably. In 1818, Mary Shelley's Frankenstein warned of the unintended consequences of artificial creation. And by 1942, Isaac Asimov explicitly formalized these anxieties into the 3 laws of robotics, the very first formal behavioral constraints for artificial agents.
These ancient texts established impartial philosophical frameworks that still perfectly map onto AI ethics today. They differentiate moral agency. Humans make accountable choices, whereas machines just compute probabilities. They establish the concept of stewardship, warning against abdicating human oversight to automated systems. And they draw a sharp line regarding omniscience, reminding us that while AI output might look infinitely wise, it's ultimately just statistical inference based on human data. It is an incredible lens for viewing the limits of created systems.
Section 5. The 1943 Convergence. So, the crucial point is, we've traced the logic, the machinery, and the ethics. Now we reach the dramatic climax. We enter the wartime laboratories of the 1940s, where centuries of isolated thoughts are about to violently collide. None of these thinkers, from the Babylonian scribes to Ada Lovelace to the ancient theologians, knew they were collaborating. But their threads were weaving together. The formal logic of Aristotle and Boole met the mechanical reality of Zeus's computers and Shannon's electrical circuits, all while framed by the ethical questions of agency and creation that humanity had debated since Genesis. They were all about to be braided together by 2 men in a small office at the University of Illinois. Because when McCulloch and Pitts published their mathematical model of a neural network in 1943, it wasn't an anomaly. 1943 was not a beginning. It was a crystallization. It was the exact moment when the formal, mechanical, and philosophical inheritances of human civilization were finally written into a single mathematical object. They proved that reasoning had a mechanizable form, bridging biology, math, and machinery all at once. Which leaves us with this final, absolutely staggering thought. If it took 6,000 years of collective human thought, from the first clay tokens in Mesopotamia to the first artificial neural network, to build the foundation of an artificial mind, what on earth will we create in the next 100 years? The foundation has been laid over millennia, but the true building phase, that has only just begun. Thank you so much for joining me on this explainer. Keep asking those big questions, and I'll catch you on the next one.